Hello everyone. In this lecture today, we are going to discuss distributed Bragg grating reflector, Bragg reflector, distributed Bragg reflector, especially the design aspects I will be discussing today. So, first I will consider using distributed Bragg reflector, one can demonstrate various kind of devices including laser, active devices, add drop multiplexers. But one of the important aspect is that it is just a reflector, a band of wavelength around Bragg wavelength can be reflected. That means that band will be stopped in transmission. So, that is why it is called band stop filter. So, I will be discussing a band stop filter, how one can design using a single mode waveguide structure. Similarly, I will be discussing the aspects of band stop filter with a multi-mode waveguide structure. So, now let us again recap the DBR structure. It is basically top view of a representative silicon or insulator waveguide structure. So, this is your waveguide, you can consider this is your single mode waveguide, this is also single mode waveguide at the output and input also single mode waveguide, but in between from z equal to 0, so from here to here z equal to L, this is z direction, there is a periodic perturbation. This periodic perturbation, you can see that rectangular perturbation structures are there in both sides, in the side wall, it is just defined in the side wall. And in this type of structure, you know that the forward propagating wave will have electric field associated to forward propagating mode is this one, and we can define also backward propagating wave because of the distributed reflections. You can generate backward propagating wave if you are considering only launching from this side also only. And this EF and EB backward propagating wave we have discussed earlier, that how that can be expressed. This A1z and A2z, that is the variation evolution of forward propagating wave and backward propagating wave respectively along as a function of z propagation direction. And you know this delta beta, that means phase mismatch factor, delta beta, that is defined by 2 omega by c. Omega is the operating frequency, omega as we know that is defined by 2 pi c by lambda, and n effective omega, that time n effective lambda you can express. So, as a whole you can express delta beta, that means propagation difference in propagation constant, that phase mismatch factor is can be expressed in terms of lambda. And this lambda, capital lambda, this is the period of the grating structure from here to here, this is the lambda period. So, all these we have discussed in earlier classes. Now, as you know, if we just consider boundary values something like that, A1z equal to 0, A10, that means I am launching here in forward direction with a amplitude A10, that means here a fixed value you are launching at z equal to 0 if you put. And then the reflection coefficient, that is small r is represented as amplitude reflection coefficient, that also we have derived using coupled mode theory, amplitude reflection coefficient. Okay. So, this is the amplitude reflection coefficient, or that can be defined as whatever backward direction amplitude is there, that is actually we call A20 divided by whatever I have launched here. So, that is your reflection coefficient for the entire DBR structure, and that is defined by this one here. When delta beta, if it is 0, that means this one, this second term in the denominator will not be there, and then in that case we know the reflection coefficient is a tan hyperbolic, so on, delta beta equal to 0, right. And reflectivity, that means intensity, power reflection coefficient, so called reflectivity, okay, this will be called as a reflectivity. Reflectivity, just you take a, this is a complex, you take complex conjugate, multiply, then you get a reflectivity. And where S is defined as kappa square minus delta beta by 2 whole square. Kappa how can be estimated, we have also discussed in the previous class. Now, if you see, just analyze this R, that means you are just taking complex conjugate of this one, this R means R star, that is actually reflectivity, and you are getting this equation. And you know, if you just put delta beta equal to 0, delta beta equal to 0, S will become kappa, okay, S will become kappa, and then delta beta second term will go, and then reflectivity, normally at delta beta equal to 0, that will be maximum, that is why we write R max tan hyperbolic kappa L, that also we have discussed in the previous lectures. Now, you see, in this function we do have two different type of functions, sine hyperbolic something x and cos hyperbolic x. X means here S times L, L is the length of the DBR structure, right. And if I want to analyze how this R varies with delta beta or any other parameter like kappa etc. or length, we need to know how the sine hyperbolic function, cos hyperbolic function looks like. You know, if you just plot sine hyperbolic, cos hyperbolic function, this is a blue curve, this is cosine hyperbolic. So, this is minimum cosine hyperbolic x equal to 1 when x equal to 0. So, that will be minimum. But in case of sine, so you have to follow this red one. So, red one, if you see that at x equal to 0, sine hyperbolic x equal to 0, and then as you go, as you increase your x value both sides, then it is just increasing to infinity, as just little bit slightly above x equal to 1, it is going very large, and at certain value you will see it is almost merging to the value of cosine hyperbolic x. So, now since it is tan hyperbolic function also we have represented, tan hyperbolic function is nothing but it is a simple trigonometric formula. We know that tan hyperbolic is hyperbolic x equal to sine hyperbolic x divided by cos hyperbolic x. So, that means if you divide this two, you get this green curve, that is actually for tan hyperbolic x. So, if x means if SL, S means this one, if kappa or delta beta defined by this, if they are detuned, then we know how the sine hyperbolic function and cos hyperbolic function varies with that parameter, and we will be eventually getting the results for power reflectivity of the DBR structure. So, now we will look a certain issue. All right, R maximum can be tan hyperbolic square kappa L. So, tan function is this one, this is tan hyperbolic function x. So, that means this kappa L tends to infinity, that means it becomes tan hyperbolic square becomes R max become 1, that is known. So, maximum value of reflectivity can be 1, that is for sure. Reflectivity, it is a fraction of power reflected from the DBR structure with respect to the input power. So, that can be maximum 1. So, as you reduce the kappa x by kappa L means this is x, this x is reduced, then your reflectivity will be reducing, and when x equal to 0, your reflectivity will be 0, right. So, when x equal to 0 means this kappa L value for delta beta equal to 0 is 0, that is possible either kappa equal to 0 or L equal to 0. In that case, your reflectivity will be 0, that is like a homogeneous waveguide, no perturbation, nothing is there. Now, I will be looking for some other issue. Let us consider what could be the minimum value of R, must be 0, right, that is what it says. So, in that case, suppose L not equal to 0 and kappa not equal to 0. L has the DBR structure has a finite length and kappa also has a finite value. So, I will investigate whether R can be 0 for any delta beta value. Delta beta can be expressed like this, or for any other delta beta means omega or n effective or whatever. Is there any possibilities there? I have learned that delta beta equal to 0, reflectivity become maximum. But then if it is maximum, there can be some other point delta beta not equal to 0. Obviously, that is should be delta beta not equal to 0. There may be a chance that reflectivity can be 0. Ultimately, you see the reflectivity sine hyperbolic cosine hyperbolic function is there. So, I would like to know the nature of the reflectivity when delta beta not equal to 0. You see, for R equal to 0, if you just try to see, just looking into the expression, it is easy to say that if sine hyperbolic s equal to 0, SL equal to, if this one equal to 0, then R will become 0. But not always. It can happen that if this equal to 0 and this value denominator part should have some finite value. If denominator itself becomes 0, then 0 by 0 it is indeterminate. So, we should be careful for choosing R equal to 0. So, for R equal to 0, we have this is 0 and this value sine hyperbolic also will be 0. I am just considering that R equal to 0, if this one 0 means this one 0, but at the same time this should not be equal to 0, that is what it is mentioned here, alright. So, looking into that, we can say that sine hyperbolic SL equal to 0, let us consider numerator, okay. Then I know sine hyperbolic x equal to e to the power x minus e to the power minus x by 2. That means sine hyperbolic 0 means e to the power SL minus e to the power minus SL by 2 equal to 0. This you little bit simplify, then what you get? E to the power SL minus e to the power minus SL, that is actually equal to 0. E to the power SL equal to e to the power minus SL. That means e to the power 2 SL, that is equal to 1. That is what it is written here. And 1 can be written as e to the power j 2 p pi, that is what it is written. So, this p you could consider, this is true for p equal to 0, 1, 2, 3 integer values, but this 0 value I would not consider. Why is that? So, this turn into the picture that SL equal to j p pi from this equation. If I compare this to this, if I put p equal to 0, L not equal to 0, L not equal to 0. If I put p equal to 0, S equal to 0. So, if S equal to 0, this part will become 0, S cos hyperbolic SL equal to 0. So, while choosing p equal to 0 and for sine hyperbolic SL to make 0, if you choose p equal to 0, then simultaneously this value will become also 0. So, that means 0 by 0 will come. That is the reason p equal to 0 value should be omitted, because that value becoming indeterminate. So, we have written p should vary from 1, 2, 3 and so on. So, for p, if you just follow this equation and with that equation p must not be equal to 0 and p should be starting from 1 to 3, then whatever value you get for that S value you get, that will result into reflectivity equal to 0. Alright. Now, you try to see that this equation is square, because it is a j imaginary term is there. So, if you just square it, then you get j square equal to minus 1, right. So, minus 1 p square pi by L, L I have taken this side. So, from this equation I get this one. And again you know A square we have defined like this while developing coupled mode theory, right. So, if you just put instead of S I just put kappa square minus delta beta by 2, then it will be p square pi by pi over L square, that is true. So, we get delta b, delta beta we have just writing for p is the integer value we are considering, plus minus this one kappa square plus p square pi square. So, I can find out for this delta beta value if it is satisfying either plus or minus of this one when p is running over 1, 2, 3. So, discrete values of delta beta solutions you will be getting where r can be equal to 0, reflectivity can be 0. So, that means I said that delta beta equal to 0, your reflectivity can be maximum, but as you keep on increasing delta beta value both plus direction and minus direction, delta beta can be plus and minus depending on this expression. If this one is larger than 2 pi by lambda, then it is a plus, if it is less than 2 pi by lambda, capital lambda, then it will be negative. So, both direction it can have solutions like this, and periodically you can see r equal to minimum. So, you can see that in principle I will show that the reflectivity normally if you just put delta beta, when delta beta equal to 0, reflectivity can be maximum, and then it can come 0, and then again another 0 will come, that means in between there will be maxima. So, slowly reducing this type of characteristics you will be getting that oscillations will be there. There is a main band and then both side you can have periodic maxima minima, and that maxima will be slowly in the reducing order. If you just plot this one as a function of delta beta, you will be getting this type of characteristics. I will show that. Okay. So, delta beta not equal to 0, reflectivity can become 0 for other values periodically, and that depends on using this equation. Good. So, to find central stop band, delta omega SB stop band, SB stand for omega, we should substitute p equal to 1, because p equal to 1 you will get delta beta, because delta beta can be expressed in terms of omega, and if I want to find out stop band, then I must find that there will be a central maxima and then positive side minima and negative side minima, then oscillations will be there, right. So, this is your delta beta running, this is your 0. So, this value, this minima comes because of p equal to 1, and then next minima come because of the p equal to 2, and so on. So, backside reverse direction also p equal to 1 minima, and then again p equal to 2 another minima, something like that. But this delta beta can be at delta beta equal to 0, reflectivity can be maximum. So, our interest is that this is the main stop band, that is the main reflected spectrum. So, if I want to know the stop band, then I need to know the value of delta beta here and corresponding omega value, delta beta value and corresponding omega value I will find, and here also I will be getting the delta beta value and corresponding omega value. Then 2 omega, you can consider omega 1, this is suppose omega 1 and this is omega 2. So, omega 1 minus omega 2 is the central stop band. That is what, to find the central stop band we have to put p equal to 1, then you get delta beta 2 values plus minus kappa square, p equal to 1 you put pi L. So, with these two value we just mention that this inside square root whatever the value is coming, that can be kappa naught. So, kappa is the coupling coefficient, we know that, but you have to add pi by L square. Obviously, if L is very large, this value can be ignored, the second term can be ignored, in that case it will be just simply 2 kappa plus minus 2 kappa. Otherwise, if L is comparable to pi or something like that, comparable to kappa, so this second term if it is comparable to kappa square, then I think you cannot ignore that. So, in that case what we get, delta beta plus I am writing, I know delta beta expression, and delta beta plus I am writing for a given omega 1 frequency here, 2 omega over c n effective, we write n effective, again n effective must be at omega 1 minus 2 pi by lambda. That will be happening because of the delta beta value of 2 kappa naught, and another delta beta minus where r equal to 0 comes, corresponding frequency must be omega 2. So, we know this expression omega 2 I am writing 2 pi by lambda, lambda is fixed, and that is happening because of the minus 2 kappa naught. So, I have this at this point plus 2 kappa naught, 2 kappa naught means this one, you can have reflectivity 0 and minus 2 kappa naught, delta beta equal to minus 2 kappa naught. So, delta beta as you know it can be plus and minus, and this 2 value you can get first minima. Within that minima, what is the frequency range? I know the omega 1 here and I know the omega 2 here. I will concentrate this expression, kappa naught known. Just subtracting these 2, I will be getting the stop band. That is what we do. Subtract this one and this one. Okay. So, if you subtract, what you supposed to get? Omega by c n effective, normally it is 2 times beta 1 omega 1, we just this one in principle omega by c n effective, that is beta, we have written beta omega 1 minus 2 beta 2. So, it is easy to write down. Earlier we have defined again and again beta equal to omega c by n effective. Okay. So, what I write here? This is beta omega 1, whatever the value beta coming at omega 1, 2 times omega 1, beta omega 1 and 2 times beta omega 2, that is subtracting, and this one when you subtract 2 pi by lambda, here it will be plus, that will be removed, cancelled, and then 2 kappa naught minus 2 kappa naught, that will give you 4 kappa naught. So, from here we get beta omega 1 minus beta omega 2, that is giving you just 2 factor, it is 2 kappa naught. This one I write as a delta beta stop band, that is what we have written, delta beta stop band equal to 2 kappa naught, that is what the expression I have written here. Okay. So, now again this is the expression we should keep in mind, I will follow this one. Again we know another expression d omega beta relationship is there for any given waveguide structure. We have a omega beta curve, how to generate, we know that at a given frequency I can find out what is the slope there, how it is varying d omega by d beta, that is actually nothing but c by n g called group velocity. So, from here if I just simply do little bit delta omega s b, then delta beta goes this side. So, in this way I can write differentially, I can write if delta beta is detuned, how much delta omega will be detuned. This is a simple omega beta relationship gives. If I know n g group index of the waveguide, then if I detune my frequency a bit, how much delta beta will be changed? I know that if we know the n g or group velocity c by n g. Okay. From this expression I can write down that okay, this delta beta can be replaced with this expression, because delta beta term is related to delta omega. So, we write delta omega equal to delta omega, delta beta instead of delta beta I will be writing here delta omega stop band equal to c by n g times delta beta naught. So, delta beta s b. So, delta beta s b is nothing but 2 kappa naught. So, I write c by 2 n g, 2 is there and kappa naught expression is this one. Okay. So, 2 kappa naught c by n g, 2 kappa naught, delta beta expression I have written here. So, I know what would be, if I know the group index, if I know the kappa, if I know the length, then I will be able to actually calculate what is the stop band, central stop band of a DBR structure. Okay. So, n g, kappa, L, these are the design parameters for the DBR structure. So, if you can design properly, if you want to get a certain stop band, certain bandwidth, you want to you do not want to pass through the waveguide structure, DBR structure. So, you can actually design and design a waveguide such that certain Ng you can get and kappa. Mainly Ng for a given waveguide structure, single mode waveguide structure, Ng does not change much. So, only you can control kappa. How kappa can be controlled? How much perturbation you are doing in the waveguide structure, more the perturbation, more the kappa value. Okay. So, depending on that I can calculate stop band centering around Bragg wavelength or Bragg frequency. We can just convert it into omega lambda relationship. We know this omega equal to 2 pi c by lambda. So, you can write delta omega equal to 2 pi c lambda square delta lambda, minus sign will be there. So, this delta omega if you just convert into lambda, then we can find out stop band in terms of lambda, lambda b square Bragg wavelength pi Ng and this one. So, you can control your stop bandwidth, how much bandwidth you don't want, how you want to reflect, you do not want to transmit them through the waveguide. So, it is a particular band, it can be a channel, particular channel, information channel you want to stop carrying carrier frequency, carrier wavelength known, then you can actually design your DBR structure. So, let us go for certain example. As I mentioned, okay, I repeated this reflection amplitude reflection coefficient, S square defined and power reflectivity and then stop bandwidth, and then you have a stop bandwidth in terms of angular frequency, stop bandwidth in terms of wavelength I know, and lambda b obviously you know how to calculate lambda b, that is for delta beta equal to 0, lambda b equal to 2 n effective period. So, you can control the period, you can find the which part, if you know the n effective index of the waveguide guided mode, and if you design a certain period, depending on that certain wavelength will be the Bragg wavelength, around that point actually delta beta will be equal to 0. Okay. Now, let us consider as it is shown top view here, if you go for cross section, then you can say that well you can have this is your total waveguide width and periodically perturb this region. This is a rib waveguide structure slab region, this thickness is called H slab and this thickness is called capital H device layer thickness, and this one we will be calling as a waveguide width. Okay. And then you are getting a perturbation from x1 to x2 lateral direction, and obviously y1, this is xy coordinate. So, this is the x coordinate and y1 coordinate, x coordinate and y1, this is x2, y2, y1 and so on, coordinate system is there. This is the region, it is perturbed periodically. Periodically it is removed the silicon, this is device layer, if it is silicon on insulator, this is silicon and this is your box layer, barium oxide layer. So, using this structure you know how to calculate kappa value, earlier we have expressed using your so called rectangular periodic perturbation, and for that purpose if we calculate kappa using coupled mode theory, you know that if it is a single mode waveguide, only one mode will be launched from this side and same mode will be reflected backward direction. So, in that case kappa will be n d square minus n c square by n effective 2 times overlap integral in this region. You have to see how much field strength, suppose you have a field like this defined like this. So, this field strength covering in the perturbed region, that is actually comes in your kappa calculation. Okay. And you need to integrate only x1 to x2, y1 to y2 in the xy plane, because beyond that no perturbation is there. So, normally to calculate kappa you need to know field strength for the two coupled modes and as well as your the region you are getting perturbation. 2 times is there because we can have two side. If I can calculate one side, that means x1 to x2, y1 to y2, that means you are calculating kappa for one side, and similar kappa you will be getting in the other side, that is why 2 times comes. If it is only one side perturbation, this side is completely filled, this side is completely filled, then you can have this, then you do not need to write this 2, just one side. Okay. Using this kappa value, using this delta beta expression and using also that expression S square equal to kappa square minus delta beta by 2 square, right. And delta beta is expressed like in terms of omega, omega can be expressed in terms of lambda. So, as a function of wavelength, if I define a period of 292 nanometer for L equal to 200 micrometer length, device length, and delta W means this perturbation, this suppose this is the perturbation, so called x 2 minus x 1 can be called as a delta W. So, one side perturbation delta W is 50 nanometer, other side another 50 nanometer. Then we can use this calculation, kappa calculation. I get kappa calculation about 0.023 per micrometer. Obviously, this one will be per micrometer, lambda is here per micrometer expression dimension. So, considering lambda equal to 292 nanometer and corresponding N effective, if you calculate for this waveguide dimension, certain waveguide dimension you considered, right, then what you get? Typical value, the Bragg wavelength you are getting exactly at 1550 nanometer for a given design, right. And then what you see, as you detune delta beta, meaning you are detuning omega or lambda, here it is lambda shown, then you see the central maxima is there, that is actually equal to 1, for delta beta equal to 0 it is 1. You are simulating, this is a plot using MATLAB code. So, you can do also, you can try how it is actually happening. So, you can find that, you see, after certain from 1550, that is actually where actually phase matching condition satisfied, where delta beta equal to 0, that is why you are getting maxima. Now, other than delta beta equal to 0, there are other values you are getting where the minima occurs according to our previous discussion. Minima means r equal to 0 occurs. So, our interest is that first 0, that side and this side. So, this is as a function of lambda you are calculating, whatever lambda you are getting here, whatever lambda you are getting here, if you subtract you get delta lambda SB, that is the stop band. So, I can have very narrow stop band depending on the design parameters like kappa or delta W, right, and also of course, length is also involved in here, length is also involved, how narrow, how broad are you want to get. So, longer the length you can get a narrower the reflection bandwidth, because L is in the denominator here. And when you see that kappa is small kappa means delta lambda SB will be smaller. So, you can get a narrow channel, narrow stop band. Some application you need broad stop band, and some application you need maybe very narrow line width channel you do not want to allow, you want to get reflected. So, that can be actually designed, that you can find out. Just you have to design your waveguide, calculate N effective, calculate NG, and then calculate the you just decide what type of perturbation is required for having a Bragg wavelength at lambda b. Once you know N effective and period, you can get a lambda b, and desired lambda b you can calculate, and accordingly the period you can set. Once it is set, then you can actually find as a function of length or kappa how the bandwidth is related. Suppose you need a very narrow bandwidth, then kappa has to be reduced to a smaller value, so that accordingly delta W you can control, this delta W how much perturbation you can control, you can get a narrower. If you want more broader and broader, you increase the kappa value, that means you are increasing the perturbation, then you can get a broader stop band. Alright. Now, you see such a device actually we have developed, we have understood the coupled mode theory now, that this is possible. Now, I have shown that some device we fabricated in our lab in IIT Madras. I see this is the how waveguide, a scanning electron microscopic image, it is shown here in the DBR region. You define a periodic perturbation and you fabricate, then finally you end up with this type of structure. Both sides it is perturbation is there. So, input side will be a input waveguide, single mode waveguide, output side will be a single mode waveguide, in between this is the DBR structure, some section of the DBR structure is shown, okay. And this will be your so called period, and that will be your from here to here, that can be your perturbation, and depending on the perturbation, or it can be considered x1 and this can be considered x2 if this is a x axis and this is the z axis, vertical direction is the y axis, and y1 y2 you can consider, and you can calculate kappa value. And you can have a DBR structure, not necessarily that you need to have both side grating, you can have one side also. For example, it is shown here that this region, if you are just taking the scanning here same image, this to this point the width is 384 nanometer, and this one around 150 200 nanometer. So, that way you can also design a DBR structure. It can be one side, it can be both side, another one sided, where actually the if you see this one here, if you see this is totally 576, same structure, same device, actually you are scanning here to see the width. So, here 384, there 576. So, delta W, that means width perturbation is 576.1 minus 384.1 nanometer. Okay. So, this is about then 192, about 200 nanometer, around 200 nanometer perturbation is there. So, such a device we have fabricated, and we have actually got the transmission characteristics. You are launching, suppose this is your DBR structure, and then grating coupler here, you launch here and you launch here, you tune the wavelength, then you see certain wavelength in transmission is missing. That means, that part, that lost energy in the transmission, that must be reflected backward direction. Okay. So, what you see, in the transmission you see 40 dB extinction, you get a bandwidth of 11 nanometer for a grating length of 450 micrometer. Yeah, delta W it is given here 190 nanometer, 575 nanometer, all the other parameters given, and you see almost nearly 1550 nanometer you get a stop band and bandwidth 11 nanometer, right. And extinction, that means this much 40 dB down. Suppose you have a laser line here, whatever value you get the intensity, and here laser line it is there, it will be 40 dB down. So, such a high extinction filter has some applications, especially in quantum photonic application and microwave photonic applications, we will discuss later. So, using the experimental results, you can find out what is the transmission coefficient. It is actually 10 to the power minus 4 only transmission coefficient. Reflectivity is 99.99%, right, r equal to 0.9999, delta lambda it is shown. So, from this experimental data we can extract lambda b equal to 2 times n effective, this one, right. And also you know from the delta lambda SB stop band expression, this one you have Ng is there. So, you know lambda b, you know kappa, you know L. So, you can find out Ng, extracted Ng we can get something like that, group index. So, from the experimental results you can find out what are the design parameters, whether that is matching with the calculations or not, you can compare. So, in our design, in this type of design and fabrication, experimental results matches very well with the coupled mode theory results. So, this is a good ploy to design a stop band filter using single mode waveguide, periodically perturbed single mode waveguide, or so called DBR structure, distributed Bragg reflector, integrated in a single mode waveguide structure. Okay. Now, let us move on to, if suppose your device is multimoded, what happens if you are still doing a DBR structure, whether you will be getting a stop band filter or some different type of filter characteristics you will be getting. So, we have shown that if you fabricate a DBR structure in a multi-mode waveguide, at least it can support 2 modes, for example. Earlier we are considering only single mode waveguide, but it is 2 mode, you get a very interesting results, and that can be useful for many applications also. I will show you some results. Let us consider this is the top view, schematically it is shown, top view of the waveguide structure designed in silicon on insulator platform, just top view you are showing. Initially input side it is a single mode waveguide. This is a single mode waveguide output side, and that single mode waveguide it is shown the propagation constant is beta naught prime, both are same. It only supports fundamental mode, assume, and in between you increase the width little bit adiabatically, so that any fundamental mode like this, if you are launching, that will be slowly adiabatically it will be expanded, so that even though it is a multi-mode waveguide structure, higher order mode will not be excited, assume at the beginning. But what happens as it propagates to the DBR structure, through the DBR structure, since it can support both the mode, fundamental mode as well as first order mode, there is a chance that forward propagating fundamental mode can couple light into the backward direction to the fundamental mode and backward direction first order mode, because it can support. So, it can this fundamental mode, whatever frequency wavelength you are launching here, that frequency wavelength can be phase matched to the backward propagating fundamental mode and backward propagating first order mode. So, once it is phase matched, and if you find their overlap or coupling strength is non-zero, so you can see that you can get reflection band, one reflection band due to the coupling between forward propagating mode to backward propagating mode, and another band you will be getting because of the coupling between forward propagating fundamental mode to with backward propagating fundamental first order mode. So, you can expect a two stop band. So, same device earlier, if it is a single mode waveguide structure and DBR structure is there, you could get only one stop band. But if it is a multi-mode waveguide, then you can get a two stop band distinctly, because they are phase matched at different wavelength or different frequencies. Okay. This is some 3D view, here it is shown input waveguide single mode, output waveguide single mode, taper such that anything launched here, that is a single mode, and as it is entered into the DBR structure, it will remain fundamental in the forward direction. But because of the phase matching condition, light can couple to the backward propagating fundamental mode and backward propagating first order mode. So, to understand that, it is shown that, for example, you have a two modes in the forward direction. In the grating structure, you have the fundamental mode is having, because it is width is large. So, this propagation constant will not same, you know, beta actually 2 pi by lambda n effective. So, width is different means n effective is different. So, for a given wavelength, beta will be different here for the fundamental mode, beta will be different here. That is why here we are considering beta naught prime and here we are considering beta naught, and first order mode we are considering beta 1. So, I can get a phase matching condition delta beta equal to 0, that means forward propagating fundamental mode beta naught minus beta naught backward propagating fundamental mode, that is why minus 2 pi by lambda. That gives rise to, if you use this expression, I can find a Bragg wavelength at lambda b 0 satisfying this one. Period is known, n effective 0, effective index of the fundamental mode known. So, you can get a Bragg wavelength here, around Bragg wavelength you can get a stop band, and another phase matching condition you can consider delta beta 0 1, that means forward propagating fundamental mode and backward propagating first order mode minus beta, that is the delta beta expression 2 pi by lambda, that must be equal to 0. Then you also get beta naught expression, beta 1 expression. If you are just using wavelength in terms of wavelength, then you get lambda b 0 1 at another wavelength, where n effective 0 fundamental mode and n effective 1 first order mode, because here you see you are putting 2 pi by lambda n effective naught, and here you will be putting 2 pi by lambda n effective 1. So, if you just simplify that one, then you get this is the Bragg wavelength for forward propagating fundamental mode coupling to the backward propagating first order mode. Now, question is that when something backward propagating mode, the beauty here earlier what we have discussed in this case, this much is lost in transmission, but where that should appear? That should appear in the reflection. But in this case, here also fundamental mode when reflect back coupled backward direction, this waveguide can support fundamental mode. So, that will appear, that means lambda b 001 Bragg wavelength which is reflected here, that will appear in the reflection, because it can support and guide back to the backward direction towards the source. You can separate them in that case. But if it is coupled to the fundamental first order mode, when that first order mode propagating in the backward direction, when it enters into the single mode waveguide, it cannot support. So, what will happen? This will be coupling to the this will be coupling to the slab. So, that means if anything coupled to the backward propagating, if forward propagating fundamental mode is coupled to the backward propagating first order mode, that backward propagating signal or energy that will not be collected by the single mode waveguide, because it is shape is like this. So, that will be lost here. So, that will be missing. In the transmission you can get two stop band, one around lambda b 00, another is lambda b 01, but in the reflection you will get only peak around lambda b 00, because that can be collected. So, that is interesting. If you are using certain this wavelength, this will be missing in the forward direction, but it will not, it will be also missing in the backward direction because of the waveguide filtering here, because this side when it is coming backward direction, the single mode waveguide cannot support the first order mode. So, that type of application we can also think of. Here it is shown that for a given waveguide, suppose your waveguide width is 760 nanometer and device layer thickness is 250 nanometer, slab height is 150 nanometer. Here this is slab height, this is your width, this is your edge. Then we can find the first two modes when you solve numerically using numerical or anything else, any numerical software if you use, simulator if you use, then you get a two fundamental mode, two modes lower order mode that is supported guided. One is fundamental mode, another is first order mode. Both the modes are T like mode. That means electric field along y direction is dominating for that guided mode. So, E naught x y means you are meaning y component, this is y component will be dominating. That means electric field will be oscillating along y direction most. Fundamental mode you see in the center it will be maximum and slowly decreasing, and there will be some kind of discontinuity just to satisfy the boundary condition. And first order mode if you see this is a blue color and this is a red color, that signifies that you are getting something like this. So, this is a positive and this is a negative, and here it will be positive, it is shown here, but it will be oscillating as a function of e to the power j omega t. As a function of time it will become positive, negative, positive, sinusoidally it will vary. So, but here at any instant of time if you see one side is positive, another side will be negative field strength, and the entire thing it is like a standing wave structure around lateral direction, and that will be oscillating as a function of time also. So, I think all of you can understand by the time whatever we have explained so far in this course. And the coupling constant, that means forward propagating fundamental mode to backward propagating fundamental mode coupling we define as kappa 00, fundamental mode is indicating as 0 here. So, it is standard whatever we discussed earlier. Coupling coefficient how to calculate we know. If we know the fundamental mode in the grating region E naught x y, whatever you are getting that one you square and then integrate one sided x1 to x2, So, if you are just suppose this region is perturbed periodically, that is what it is mentioned, and you get kappa 0 0. And if you want to get kappa 0 1, meaning forward propagating fundamental mode and backward propagating first order mode, how they are coupling. So, in this case, instead of n effective 0 here must be it is 0. You get n effective 0 and effective 1 square root mean value. Okay. So, this geometric mean, if you use that from the coupled mode theory, this comes, I think once we have discussed that, and then we can have a overlap between E naught to E 1 star first order fundamental mode. So, just one thing you should keep in mind, that if the same waveguide, if grating perturbation is both side is there, then this kappa 0 1 would be 0, because you have one side positive, another side negative. Here suppose this side is positive perturbed region and this side is positive. If you integrate, you get a positive value, but if you multiply this one and this side multiply, you will be getting negative. So, one side, one half integration gives you positive overlap, another side it will give you negative overlap if you calculate this one. As a result, the kappa you will be getting 0. So, even if it is a multi-mode structure, it can support 2 modes, but if grating is symmetric, both side wall perturbation is there, in that case you may get phase matching condition with the backward propagating fundamental first order mode for a certain wavelength, but kappa will be 0. That means coupling between forward propagating mode to backward propagating first order mode, forward propagating fundamental mode to backward propagating first order mode is 0. So, that is the reason if you want to get an active stop band, effective stop band, because of the coupling between forward propagating fundamental mode with backward propagating first order mode, in that case the grating you must fabricate, define in one of the side wall. Okay. So, that is very important for silicon photonics especially. Right. Any waveguide structure, that is true. Obviously, it is widely used in silicon photonics because the side wall grating definition is very easy using lithographic technique, standard CMOS compatible lithographic technique, etc. Okay. Now, how to design that I want the Bragg wavelength lambda be 0 0 at a certain wavelength, lambda be 0 1 at a certain wavelength. You remember that if you try to find out which one will be higher, lambda be 0 0 or lambda be 0 1, definitely n effective 0 greater than n effective 1, we know that. So, that means lambda be 0 0 is greater than lambda b 0 1. If you subtract that, what you get? You get n effective 0 minus n effective 1 times lambda. So, if you see difference between effective indices of the fundamental mode as well as first order mode, that actually defined how much separation will be the stop band. So, we need to calculate, we can design with this difference can be controlled by controlling the design parameter of the waveguide structure. So, we have calculated as a function of waveguide width for a given h equal to 250 nanometer device layer, and here we have calculated for 3 slab height effective index calculated. This is for fundamental mode as a function of width, effective index how it is increasing for h equal to 150 nanometer, it is shown 10 nanometer below and 10 nanometer, this is 10 nanometer below and this is 10 nanometer, 3 different structures, 3 different design of the slab height. You can see that for a wider width, even this is insensitive to the slab heights. All 140 nanometer, 150 nanometer, 160 nanometer slab heights for a wider width, that is almost closer to the bulk. So, that is the reason this 10 nanometer variations of the slab height would not, you would not see any effective index changes of the fundamental mode. And then as you know, up to this much width you will not see any second mode is supported. If you just increase the width, then you get another mode appearing. Obviously, again for 3 different slab height we can see their effective index for the first order mode. And if you go up to 1.1 micrometer for h equal to 250 nanometer and h equal to in this range, small h equal to in this range, the waveguide will support only 2 modes, and this both 2 modes are T like mode as I mentioned for this slab height. If you change slab height dramatically, maybe h small h equal to, suppose h equal to 0, then you can see that TM modes also will be coming into picture, not only T mode. So, in that case I can actually define, for example, if I define a waveguide width here. So, I see that difference between effective index of the fundamental mode here and this much, but if I design the waveguide width here, so this difference is this one. So, that means depending on the waveguide width, alone waveguide width variation can control this value. By controlling that, actually you can get what is the separation between 2 stop band could be, right. So, here we have just shown that okay, as a function of width, just calculating that lambda b 00 as a function of width, where it will be there at the longer wavelength, and lambda b 01 it will be at the shorter wavelength. We find that okay, this is the region where actually the bottom region actually called C band, and above region above 1565 it is called L band, above less than 1565 nanometer, that is called C band, optical C band and optical L band. So, we now learnt that it is a possible, it is a really possible to design a device using distributed Bragg grating, in which you can get 2 stop band in transmission. Out of this 2 stop band, one band will be reflected backward direction, that is associated to the coupling between forward propagating fundamental mode to backward propagating fundamental mode, but the coupling between forward propagating fundamental mode to backward propagating fundamental mode, that will be missing in the reflection mode, because backward direction first order mode will not be supported. So, now let us look simulation result. We have just considered H equal to device layer equal to 50 nanometer, W equal to 710 nanometer, supporting 2 modes, H equal to about 150 nanometer slab height. Both the modes are T like mode, we know that, we have simulated earlier, we have shown the results earlier, and we find that really 2 stop band. This is a just simple simulation using FDTD technique, that is available for also commercial softwares available, finite difference time domain technique, that means a solver, Maxwell solver in time domain. Okay. So, you find that one stop band around this one around 1600 nanometer and the stop band here. And beyond this shorter wavelength region, you see it is not really picking something like this. What is the reason? Because at shorter wavelength, the waveguide itself is somewhat DBR structure actually somewhat coupling light to the slab modes, that is why it is being lost also in this region. But if you just design maybe waveguide so tightly that a little bit wider waveguide if you use instead of 710 nanometer, say 1 micron, something like that, then you could see something characteristics like this. You would be getting something like this, and then this, and then this, like this, 2 different stop band, and after a long wavelength towards the shorter wavelength, you would see somewhere that is coupling to the slab. So, wider bandwidth, wider width of the waveguide helps to get a very good distinct stop band with some pass band in both sides and in between also. Okay. But you have to be careful that if you are going for higher waveguide width, then you can eventually end up with guiding another mode. So, in that case you can expect one more stop band also, that means that particular stop band at some other frequency, at some other wavelength it will be phase matched, and in that case you can get another multiple stop band you will be getting. So, depending on the number of modes and phase matching condition, you can get multiple stop bands in the transmission. But in reflection, only fundamental mode will be supported, because input waveguide and output waveguide you are designing single mode waveguide structure, because most of the integrated photonic device structures, they are designed with a single mode waveguide. Only in the DBR structure, if you want this type of some specific application I will explain also, if you want to get this type of transmission spectrum, then you go for this device. This is easy design basically. And you see here, there is another one curve is also shown. If you just increase the device temperature a bit, then refractive index of the silicon increases, and because of that your N effective also increases. So, lambda B equal to 2 N effective period. So, when N effective will slightly increase due to the temperature, that is called thermo-optic effect. Silicon is a very good thermo-optic effect. Here 25 Kelvin temperature, if you increase, then you see the Bragg wavelength, fundamental mode stop band and first order stop band, both will be actually rate shifted 2.2 nanometer. Rate shifted why? Because N effective increases as you increase the temperature, effective index or bulk silicon refractive index will be increased. So, that is why it will be looking like that. And another thing, it is also experimentally found that very interesting, that instead of keeping the waveguide surface free, empty, air, you get a particular characteristics like this one. But now if you put a drop of water, so the top cladding is water, and water refractive index, you know, in water is about 1.3 and in air is 1. So, that means cladding refractive index is increased. So, once the cladding refractive index increase, N effective will also increase. So, that is how when air is given as a cladding of the waveguide structure, you see the rate shift happening, this rate thing, this is the thing, both fundamental stop band and first order stop band rate shifted, and rate shifted about 7.8 nanometer, 6 point, this case it is measured at 6.9, one is about 6.6 nanometer, because N effective for fundamental mode and N effective for first order mode, they do not increase equally because of the cladding refractive index change. So, by changing the refractive index in the cladding material, you can change the characteristics, detune the characteristics, but this eventually people exploit it for sensing application. Suppose you have certain liquid and you know that has certain liquid will have certain refractive index, and you do not know what is that material. So, you can guess, just use that material in that liquid in the top or coat in the surface, and then you see the Bragg wavelength, how much it is shifted, and looking into the shift you can estimate that you can actually find, you can try to guess what material could be in the surface. So, for biosensing applications etc., people are demonstrating different type of DBR structure in silicon photonics technology platform. Okay. Now, I will show you that such device also fabricated. Here it is shown, you see 560 nanometer and perturbation, that delta W 150, so about 710 nanometer. So, this is W equal to 710 nanometer, it is approximately supporting 2 modes, and in this case it is 760 nanometer W. So, it also supports 2 modes, and we have fabricated device, this fabricated SEM structure it is shown here, and it is characterized, this is input grating coupler, output grating coupler, DBR structure is there, around 5 millimeter long waveguide fabricated, and this is about 450 micrometer grating structure fabricated. So, when it is coming and going, and if you are tuning your tunable laser source wavelength you are tuning, then you see if there is no DBR structure, reference waveguide would show this type of characteristics. Wavelength dependent coupling is there in the grating coupler, that is why you see the difference as a function of wavelength, this is the transmission. But when grating structure is there, you see there is one stop band here, another stop band is here, and this region actually lost because of the coupling to the slab mode. Okay. So, this is actually this region, actually your region where 1565, this side is called, sorry, this side is so called, this side is L band and this side is C band. So, you could see that L band will be passed through the DBR structure, C band can be stopped completely. So, if you want to have certain band, broad band, if you want to stop, you do not want to allow to transmit in a certain destination, then you use this device. Only this band wavelength range up to here it will be passed. Again this range it will be stopped. So, some unwanted band if it is there, you can stop here both sides, only a selected band you can transmit. So, you can design a device something like that, that a selected band will be passed. It is a DBR structure, normally it is used for stop band, but in this case you can have a 2 stop band, wide broad stop band. Here if you see, it is more than 15 nanometer stop band, this side also more than 15 nanometer, even beyond. But in between you get about from 1565 to 16, about 30 nanometer bandwidth it will be passed. So, you can selectively a certain bandwidth you can actually transmit through silicon waveguide structure or DBR structure. Okay. So, I stop here for this lecture today.